Today we are going to be introducing the concept of transient analysis. And in Circuits 1, we're only going to be dealing with what are called first-order circuits. A first-order circuit is a circuit that contains one independent energy storage element. So that might mean a circuit that contains, say, a single capacitor and some resistances, or a circuit that contains a single inductor or some resistances, or circuits that contain multiple capacitors, but we can simplify it down to a single equivalent capacitance with some resistance, or a circuit that contains multiple inductors, but we can simplify that inductance down to a single equivalent inductance with some resistance. For our intents and purposes in Engineering 221, we will not be dealing with circuits that contain both inductors and capacitors from a transient analysis perspective. So, I would like to introduce what the concept of a transient condition is by looking at a couple of very simple circuits. So, let's consider the following simple circuit. We have some source voltage, Vs, and we're going to introduce a switch. And this switch is going to be opening at t is equal to 0. Connected to my voltage source and switch, I'm going to put some resistor that has a value of R. And my goal is to develop a relationship. Sorry, confusing myself here. Here's R. So I want to develop a relationship for the resistor voltage as a function of time. And I know that this particular circuit is trivial, but it's going to help us illustrate something. All right? So we have, in essence, two distinct circuits. One for all t less than 0 when the switch was closed, and one for all t greater than 0 after the switch was opened. So if we plotted the voltage drop over the resistor as a function of time, it should be fairly easy to see that for all time less than 0, when this switch was closed, so we can treat it like a short circuit, the voltage drop over our resistor was Vs. So we have a constant value. Right? This is what's known as a DC steady state condition. After our switch is opened, we have an open circuit here, and we should observe that the voltage drop over our resistor instantaneously drops down to 0. So we have another DC steady state condition, right? So we see that our voltage is constant until we interrupt that voltage supply by opening that switch, and then we see that our voltage immediately falls down to 0. So we have a DC steady state condition on the left-hand side of 0, and another DC steady state condition on the right-hand side of 0, okay? So this circuit does not have any what are called transients because there is no transition time between DC steady states. We have DC steady state on the left-hand side of 0, we have DC steady state on the right-hand side of 0. But I can change this circuit slightly. Let's say that now I put some capacitor in parallel with my resistor. And let's define this voltage, instead of just being the resistor voltage, to be V of t, which is the voltage drop over the resistor, which is in parallel with that capacitor, okay? Well, let's make our plot again. Again, it should be intuitively obvious that when this switch is closed, up into the moment right before it opens, the voltage drop over the resistor and the voltage drop over the capacitor needs to be Vs of t. So it's going to have some constant value. And again, we are seeing a DC steady state condition. After we open the switch up, what should we expect to happen? Well, we're still looking at the voltage drop over a resistor, and we saw that when we interrupted the supply voltage, the voltage drop over the resistor went down to 0 instantaneously. The problem we have with that is if we look at the capacitor current. So I'm going to define my capacitor current to be in this direction, down, so that the current is flowing into the positive polarity terminal. Hopefully you all recall from our lecture on capacitance and inductance that IC of t is equal to C times the derivative of the capacitor voltage, which in this case is dV, by dt. If this voltage abruptly changes from Vs to 0, this derivative approaches infinity. Now you may say, well, what's really the problem with that? One, we can never actually achieve an infinite amount of current, right? An infinite amount of current would mean that we are required to transfer an infinite amount of charge in an infinitesimal amount of time, which cannot physically be done. And if we followed this capacitor current around, this is an open circuit here. So we know that no current is going to flow through this voltage source. So all of that capacitor current should be flowing through this resistor, which means that our voltage V of t is somehow both 0 and negative infinity at the same time. So we have a fundamental problem here, okay? So one thing that we can observe from this relationship is that the voltage drop over a capacitor cannot change instantaneously because it causes an infinite amount of current to flow. So let me write that down explicitly. Abruptly. So what this means is that the voltage drop over our capacitor at t is equal to 0 minus has to be the exact same thing as the voltage drop over our capacitor at t is equal to 0 plus. If we have a discontinuous voltage waveform over our capacitor, we are in essence forcing an infinite amount of current to flow, which cannot happen. So now let's say we know that V of t has to be equal to V of s on the positive side of 0, right? But if there's no source connected to the circuit, we should see that eventually the voltage drop over that capacitor is going to fall or decay to 0. So I'm going to draw over here, and this is going to seem silly, but I'm going to put for, say, t is equal to infinity and greater. We have another DC steady state condition. So what I am trying to explain is that Let's talk about the instant that t is equal to 0 minus, okay? There was a voltage drop over the capacitor, which means that there was energy stored by the capacitor. Since the energy stored by a capacitor is 1/2 CV squared, if V is non-zero, the energy is non-zero. Over some amount of time, the energy stored by this capacitor will be distributed to this resistor and transformed into heat. So we're never losing energy, we're effectively just bleeding it off as heat until such a time occurs that the voltage drop over the capacitor decays to 0 and we are at steady state again. This time between these two DC steady state conditions is what's called a transient condition. And it's our job to mathematically figure out what's going on between t is equal to 0 plus and t is equal to infinity in these circuits. So, let me modify something real quick. So I'm defining my resistor current as down, my capacitor current as also down, so that these currents are flowing into the positive polarity terminal. If I write a Kirchhoff's current law equation at this node during the transient condition, so after my switch is opened, I should observe that IR of t plus IC of t is equal to 0. Kirchhoff's current law is valid for any and all points in time. Now, I can express IR of t and IC of t in terms of this common voltage V of t. So Ohm's law tells me that IR of t is 1 over R times V of t. And our current voltage relationship for our capacitor tells me that IC of t is C dV by dt. This is what's called a first order differential equation, okay? And we're going to have to solve this for V of t to understand what's going on during that transient condition. So we need to make an educated guess as to what form that voltage will take. And by that I mean what type of mathematical function satisfies this equation. So we have some coefficient multiplied by a function plus some coefficient multiplied by the derivative of the function is equal to 0. So our requirements here really are that V of t and the derivative of V of t need to be effectively identical functions. And the only mathematical type of function that satisfies that condition is an exponential function. So we are going to make an educated guess. We are going to guess that V of t will be of the form A, some coefficient that we'll have to determine, e to the s. S is the eigenvalue or the natural frequency of the system, t. So we are supposing here that there is an exponential relationship that is going to occur from this point at t is equal to 0 plus to this point at t is equal to infinity. If we substitute this relationship or our guess value in, we get 1 over r a e to the st plus s times c a e to the st, where this s comes from taking the derivative of my exponential function, is equal to 0. And I can rearrange this expression. There's a common factor of a. So I have a, then I have s times c plus 1 over r, and a common factor of e to the st is equal to 0. So if this function, or excuse me, if this factor A is 0, that is effectively what's called a trivial solution, meaning we are assuming that our voltage was never non-zero, which actually doesn't make sense because we know that it was something. So that's a trivial solution, effectively saying if we never excite the system, then the answer is 0. E to the st could approach 0 if s was negative, but it will never actually reach 0. And it wouldn't be valid for all time in any case. So we have a characteristic equation here, SC plus 1 over R, that we need to be able to set to 0. So SC plus 1 over R will equal 0 when S is equal to negative 1 divided by RC. So if the natural frequency of our system is then negative 1 over RC. So we have A, E to the negative T divided by RC. To calculate this value of A, we need to think back to our initial conditions, right? We said that since the voltage drop over our capacitor cannot change abruptly, at T is equal to 0 minus, our capacitor voltage had a value of Vs. And at T is equal to 0 plus, our capacitor voltage had a value of Vs. So if we evaluate this expression at T is equal to 0, then we would have E to the negative 0, which is 1. And so we see that this needs to be our initial condition on our capacitor voltage Vs. So we have Vs E to the negative T divided by RC. And I'm going to slightly more generalize this to be V at T is equal to 0 plus E to the minus T divided by RC. So this is how our voltage is going to behave. We are going to see that it's going to start at some value, which in this case was Vs, and then it is going to decay exponentially over a long period of time until it settles to approximately 0 at T is equal to infinity. So we have just determined what our voltage drop, at least over our capacitors, is going to look like in any first order circuit, because we did this for a generic resistance and a generic capacitor value, right? We didn't use numbers anywhere. We know that for any first order RC system that contains a resistance and a capacitance, it's going to behave in this way. Now, if we wanted, let's say that resistor current, we know what V of T is. Our resistor current, IR of T, is given by Ohm's law. So that's going to be V of T divided by R. So that's going to look like, I'm doing this as a piecewise function, Vs over R for T less than 0 minus, right? So we're saying the current flowing through our resistor was just Vs divided by the resistor value. It was a constant value for all time before our switch opened, and for all time after our switch opened, it's going to look like Vs divided by R, e to the minus T divided by RC for t greater than or equal to 0 plus. So we can well define the behavior of the capacitor and resistor voltage for all time, as well as the resistor current. Now I want to point something out here, and that is that the current flowing through the resistor is of the same generic form as the voltage drop over the resistor and the voltage drop over the capacitor. Kirchhoff's current law and Kirchhoff's voltage law are what's forcing this to happen. So if we see that the voltage drop over the capacitor is an exponentially decaying function, then the current flowing through the resistor has to be of an exponentially decaying function as well due to Ohm's law. And Kirchhoff's current law tells us that this current IR of t is going to be negative IC of t. And so if this is an exponentially decaying current, this has to be an exponentially decaying current as well. So we can say generically for our first order RC circuits, Y of t, where Y of t represents any resistor voltage or current and any capacitor voltage or current, will be of the form Y at 0 minus for t less than 0 minus. So at DC steady state, it has a constant value. And it is Y at 0 plus e to the minus t divided by RC for t greater than or equal to 0 plus. So for all time after our switch is opened, we see that it starts at some value and exponentially decays to 0 as time increases. So this is our generic form for our first order RC circuits. And this is a very important equation. This is what will allow us to analyze any quantity in an RC transient analysis circuit. When we come back, we will be working an example problem that illustrates this point. So this is our first example problem that we are going to work where we can apply what we've learned about the transient analysis of RC circuits to vastly simplify our analysis of this circuit. So we're going to take this problem in simple, easy to digest steps. And if you do these problems using these steps in the correct order, you'll get the right answer every time. That's one of my favorite things about these types of problems, is that it's a very simple algorithmic approach. If you follow the directions and you do your rudimentary circuit analysis correctly, you really can't be wrong. So our first step is going to be to analyze our circuit at t is equal to 0 minus. So in this case, at t is equal to 0 minus, our switch is opened. So we're told that it's open and then it's closing at t is equal to 0. Again, at t is equal to 0 minus, we're at DC steady state. So what that means is that our capacitor is going to be replaced by its DC steady state equivalent, which is an open circuit. So here will be our capacitor voltage, VC at 0 minus. Here's our 50 ohm resistor. This is our current I1 at 0 minus that we're interested in. Here is our 200 ohm resistor. Our current I2 at 0 minus we are interested in. Our switch is going to be replaced by an open circuit, so I'm just going to leave it out for right now. And then here is our current source, 0.1 amps. All right, so we're analyzing this circuit, which is how our original circuit looks at t is equal to 0 minus, for these three quantities, the voltage drop over the capacitor, the current through the 50 ohm resistor, and the current through the 200 ohm resistor. So let's start with the current through the 50 ohm resistor. I1 of 0 minus. So this 50 ohm resistor is in series with an open circuit. So by inspection, we can see that the current flowing through our 50 ohm resistor has to be 0 amps. This means that our current flowing through our 200 ohm resistor has to be 0.1 amps. So all of the current provided by this source will flow through the 200 ohm resistor because none of it can split off and flow through the 50 ohm resistor. Lastly, we see that VC at 0 plus will be equal to the voltage drop over the 200 ohm resistor, right? If we wrote a Kirchhoff's voltage law equation, since no current flows through the 50 ohm resistor, there's no voltage drop over the 50 ohm resistor, and so VC is equal to the voltage drop over the 200 ohm resistor, which is 0.1 amps times 200 ohms gives us 20 volts. And we've gotten all three pieces of information that we need to find for t is equal to 0 minus, So I'm going to write these down over here. I1 at 0 minus is equal to 0 amps. I2 at 0 minus was equal to 0.1 amp. And VC at 0 minus was equal to 20 volts. Our next step is to analyze the circuit at t is equal to 0 plus. So now we're looking at the circuit the exact instant in time after that switch is closed. So our capacitor is no longer going to look like an open circuit because we are no longer at DC steady state. We are in our transient condition, okay? So we are going to replace that with something, and I'm going to talk about that in a moment, but let's redraw the rest of the circuit real quick. So here will be our 50 ohm resistor, where this is our current I1 at 0 plus. Here is our 200 ohm resistor, where we have I2 at t is equal to 0 plus. Our switch is closed, so it is a short circuit. And then here is our 0.1 amp current source. All right, so let's revisit what's going on with this capacitor right here. So what we know about the capacitor at this very explicit instant in time, where the switch has just closed, is that the voltage over it has to be 20 volts, because the voltage drop over a capacitor cannot change abruptly. So we know that there is 20 volts drop over it for sure, but we don't know anything about the current. We know that the current can be anything it needs to be. So what I'm going to do is I'm going to, at this exact instant in time at t is equal to 0 plus, model my capacitor as an independent voltage source, because I know that it has a fixed amount of voltage and that any amount of current that needs to flow through it can flow through it. So again, I want to be very, very clear here. I'm not replacing my capacitor with a voltage source. I am modeling its behavior at this very specific instant in time as a voltage source. So here's my representation of a capacitor at t is equal to 0 plus, where it will have the same polarity that I had as defined before, so positive polarity on top, and the voltage will be 20 volts plus minus VC at 0 plus. So I can't harp on this enough because it's a common mistake. VC at 0 plus has to be 20 volts because the voltage drop over the capacitor cannot change abruptly. If it was 20 volts at t is equal to 0 minus, it must be 20 volts at t is equal to 0 plus. Excuse me. All right, so now we need to figure out what I1 at 0 plus is and I2 at 0 plus is. So we're going to have to look at what's happening here, okay? So our capacitor has 20 volts across it. And this is all one large node that I've outlined in blue, okay? So this 0.1 amp source, all the current that it produces is going to flow through this short circuit and it's going to circulate around that loop, right? None of this 0.1 amps of current can branch off and flow anywhere else because that short circuit is there. The current that's leaving our 20 volt source, it's going to flow through the 50 ohm resistor in the opposite direction as we have defined I1, and then it's going to hit this node with that short circuit. So none of this current is going to branch off and flow through the 200 ohm resistor. It's all going to flow through the short and then come back around. So from this, we can see that I1 of 0 plus is 20 volts divided by 50 ohms. And I need to have a negative sign because the current is flowing out of the positive polarity terminal. Effectively, the capacitor is acting like a source to this 50 ohm load at this point. So I need my negative sign because this purple current is in the opposite direction as how I've defined that. And so this is going to, let's see, 20 over 50 is 2 over 5 is negative 0.4 amps. If I did my math correctly there. And I2 at 0 plus is 0 amps by inspection. Again, none of the current from the 0.1 amp source will make it past the short circuit, so it's all going to flow through. And all of the current that's being supplied by the capacitor is also going to skip over the 200 ohm resistor and flow only through the short circuit. So these are our three quantities at t is equal to 0 plus. So we have I1 at 0 plus is negative 0.4 amps. So notice the current through our resistor has changed abruptly. That's perfectly okay. The only quantity that we're dealing with in this circuit that cannot change abruptly is the voltage drop over our capacitor. I2 has changed from 0.1 volts down to 0 amps, 0.1 amps down to 0 amps. And our voltage drop over our capacitor, VC of 0 plus, must remain 20 volts. So we have successfully determined all three of our quantities in question for the circuit at t is equal to 0 plus. Our next step is to determine CEQ and REQ during the transient condition. All right, so I want to talk about this for a moment. This is our original circuit. During the transient condition means after this switch has been closed. So what we are trying to find is the Thevenin equivalent capacitance from the perspective of the resistance of the circuit during the transient condition and the Thevenin equivalent resistance from the perspective of the capacitance during the transient condition. So for this circuit, CEQ should be very easy to determine because there's only a single capacitor in the circuit. So CEQ is equal to 20 microfarads. There's only one capacitor there, it has to be that. To determine our equivalent resistance, we are going to disconnect our capacitor from our circuit because we're finding the Thevenin equivalent resistance with respect to that capacitor, and we're going to look in through those terminals that are created when we remove the capacitor during the transient condition. So we're finding the Thevenin equivalent resistance. By definition, the Thevenin equivalent resistance is found by looking into the terminals of a dead network. That's why I have disconnected my current source, because we turn a current source off by replacing it with an open circuit. So I'm looking in through this set of terminals where my capacitor was and trying to find REQ. And looking at this network, we can see that this short circuit is in parallel with this 200 ohm resistor, which means the 200 ohm resistor will not contribute to the resistance. And so REQ is equal to 50 ohms. So we know what CEQ is, and we know what REQ is. Our last step, let me write these down. 20 microfarad. Let's see, 50 ohms. So our last step is simply to plug in the information that we've collected to our generic equation. Where our generic equation was y of t is equal to y at t is equal to 0 minus for t less than 0 minus, and y is equal to 0 plus for t greater than or equal to 0 plus. So let's start with our capacitor voltage. Our capacitor voltage as a function of time will be 20 volts and it'll be 20 volts, 20 e to the minus t divided by r times c. Oh, I have made a mistake up here. I'm sorry. E to the minus t divided by rc for t greater than or equal to 0 plus. All right, so r is 50. C is 20 times 10 to the minus 6. So 50 times 20 is 1,000 times 10 to the minus 6. So that's the same as 10 to the minus 3. Excuse me, I thought. 20 times 10 to the minus 6 times 50. Yes, it's 10 to the minus 3. I just wanted to make sure here. And this is going to be in units of seconds. For t greater than or equal to 0 plus. What I personally like to do, so I have 10 to the minus 3 in the denominator. I like to write it in the numerator, so 1 over 10 to the minus 3. is 1000, I believe. Yep. So instead of writing t divided by 10 to the minus 3, I can write this as t multiplied by 1000. So 1000 t volts. And so that is my capacitor voltage. My current I1. So my current I1 of t, it was 0 amps at t is equal to 0 minus. So we'll have 0 amps, t less than 0 minus. We will have negative 0.4 e to the minus 1000 t amps for t greater than or equal to 0 plus. All of our signals are going to exponentially decay at the exact same rate. Again, it's because of Kirchhoff's voltage law and Kirchhoff's current law. And I2 of t was 0.1 amps for t less than 0 minus, and it is going to be 0 e to the blah, 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 which 0 multiplied by that exponential function just looks like 0 amps for t greater than or equal to 0 plus. Now, you may be asking yourself, well, gosh, it seems very convenient that we can just use that generic equation and not have to do any real circuit analysis or calculus or anything like that with all of these transient conditions going on. Well, we can check our work actually pretty easily here. Notice that I1 of t is the same as the current that's flowing through our capacitor. So, I1 of t is C dVc by dt. So that would be 20 times 10 to the minus 6 amp seconds per volt multiplied by 20 volts, and then multiplied by a factor of negative 1000 per second e to the minus 1000 t, where these volts cancel each other, seconds multiplied by per seconds cancel, and so we're going to have 20 times 10 to the minus 6 times 20 times negative 1000 gives me negative 0.4 e to the minus 1000 t amps. So we got the exact same result, which this was a great way to actually check whether or not our methodology worked. So finding out how the capacitor behaved allowed us to calculate the capacitor current, or we could just look at it from the perspective of the resistor and simply plug things in from our into our generic equation and get the exact same result. Our next example that we're going to work is going to step up the difficulty level a little bit by introducing a dependent source. This is our new circuit that we're going to be analyzing, and as you can see, the level of difficulty, or complexity at least, has definitely stepped up quite a bit. We have a current-controlled current source that we are going to have to deal with, and our goals are to determine the capacitor voltage Vc of t as well as this resistor current I1 of t. The steps that we are going to do to solve this are going to be the same, but there are going to have to be some concessions made, particularly with finding the equivalent resistance of the circuit because of this dependent source. So as before, step one was to analyze the circuit. Analyze the circuit at t is equal to 0 minus. So at t is equal to 0 minus, our switch is closed. So we have a 12-volt source connected to a 10 kilo ohm resistor. Here is our 20 kilo ohm resistor. This is our current I1 at 0 minus. We have another 10 kilo ohm resistor. We have our dependent current source, 0.6 I1 at 0 minus. And let me write that on the other side so that I'll have room. 0.6 I1 at 0 minus. And here is our capacitor voltage, VC, at 0 minus. So to solve for this is going to be arguably a little bit more difficult than our previous example. I'm going to choose to use nodal analysis. And the reason why I'm using nodal analysis over mesh analysis is because getting the voltage drop would require getting the voltage drop over my dependent source, which is just going to be mildly annoying at best. Whereas I could use my nodal voltages to determine the current through a resistor very easily. So I'm going to set the bottom node as my reference. And this is going to be node A, and this will be node B, where VB is the exact same thing as my capacitor voltage at t is equal to 0 minus. So if I perform KCL at node A, I get, so let's see, KCL at node A. I get VA minus 12 volts divided by 10 kilo ohms plus VA over 20 kilo ohms plus VA minus VB over 10 kilo ohms is equal to 0. If I do KCL at node B, I'm going to have VB minus VA over 10 kilo ohms. Actually, minus, sorry, because the current is flowing in, minus 0.6 I1 is equal to 0. And I can get another equation, as it were, where I can say that my current I1 expressed in terms of my nodal voltages is just VA over 20 kilo ohms. And so I'm going to solve this using my calculator. So let's just say VA is equal to something, VB, which is equal to VC at 0 minus is equal to something. And I'm going to set it up 3 equations, 3 unknowns, so that my calculator will tell me what I1 at 0 minus is directly. So nodal analysis, 3 equations, 3 unknowns system will get me everything I need to know. So give me just a moment, please. So a 3x3 system where I'm going to have 1 over 10,000 ohms plus 1 over 20,000 ohms plus another 1 over 10,000 ohms. That's my coefficient for VA. My coefficient for VB is negative 1 over 10,000 ohms. There is no I1 in this equation, so my coefficient for that will be 0. And my constant term will be 12 divided by 10,000. For my second equation, I'm going to have negative 1 over 10,000. For my coefficient for VA, my coefficient for VB will be positive 1 over 10,000. And my coefficient for I1 will be negative 0.6 is equal to 0. For my third equation, I have 1 over 20,000 is my coefficient for VA, 0 is my coefficient for VB, and if I move this I1 to the other side, I have negative 1 as my coefficient for I1 is going to be equal to 0, and solve, and I get VA is equal to 10 volts, VB is equal to 13 volts, and I1 is equal to 1/2 of a milliamp. Make sure I got all my signs right. Positive 10, positive 13, positive 1/2 of a milliamp. All right, so I'm going to go ahead and write down my pertinent information over here again. So VC at 0 minus is 13 volts, and I1 at 0 minus was 1/2 of a milliamp. So that's my circuit analysis for T is equal to 0 minus. Step 2 is to analyze the circuit at T is equal to 0 plus. If I'm not mistaken, this is actually going to be a little bit easier. Let's see. Just redraw it, the whole thing. Alrighty, so at T is equal to 0 plus, this switch has opened. So I'm drawing my 12 volt source kind of just for the heck of it because it's not actually influencing anything whatsoever in the circuit. But I should have an open circuit like so because my switch is open. And here's my 10 kilo ohm resistor. Here's my 20 kilo ohm resistor. This is my current I1 at 0 plus. This is my 10 kilo ohm resistor. And then I'm going to replace my capacitor like I did in the last example with a independent voltage source having the same polarity as VC. So it's positive on top, negative on bottom, and the same magnitude as VC at 0 minus, which we determined to be 13 volts. So this is my circuit as it appears at T is equal to 0 plus, where this is my capacitor voltage. And we know by inspection that VC at 0 plus has to be 13 volts. Again, the capacitor voltage cannot change abruptly. So if it was 13 volts at T is equal to 0 minus, it must stay 13 volts at T is equal to 0 plus. Now comes how we are going to solve for our resistor current I1 at 0 plus. My intuition tells me that the voltage drop over this 0.6 times I1 current source is 13 volts because those two elements are in parallel. So that means the voltage drop between this point in the circuit and this point in the circuit is 13 volts. So I feel strongly that I could use 13 volts divided by 10 plus 20, 30 kiloohms should give me my answer for I1 at 0 plus, just using effectively Ohm's law. That being said, the presence of the dependent source worries me a smidge, so it may not be the most efficient method to go with, but I'm going to use mesh analysis to just make sure that my intuition is correct. So to be clear here, my guess is I1 at 0 plus 13 volts over 30 kiloohms is 0.433 milliamps. But those darn pesky dependent sources, I know they worry students a lot, and sometimes they worry me too. So let's brute force it using mesh analysis. So let me define my mesh currents. Well, actually, my first mesh current equation, we'll see. So this will be my mesh current. Let's call it IA. This will be my mesh current IB. So performing Kirchhoff's voltage law around the super mesh, because I have an interior current source, gives me 20 kiloohms times my mesh current IA. Remember, this is an open circuit, so there will not be a mesh current circulating around here, plus 10 kiloohms times mesh current IA plus 13 volts is equal to 0. So that's around my super mesh. Then I can see that IB minus IA is 0.6 I1. So that's my relationship for this dependent source related to the mesh currents. And lastly, I need to express I1 in terms of my mesh currents, where I1 is negative IA. All right, so those are my three equations for my mesh analysis here. So if I solve this system, I'm going to get IA is equal to something, IB is equal to something, and lastly, I1 at 0 plus is equal to something, and that's what I'm really interested in here. System, 3x3 system. So my coefficient for IA is going to be 20,000 plus 10,000. There's going to be no coefficient for IB in my first equation. There's going to be no coefficient for I1 in my first equation. And I put negative 13 volts into here. For my second equation, I have negative 1 IA, positive 1 IB, negative 0.6 I1 is equal to 0. My last equation, I have, if I move this IA over, I have 1, 0, positive 1, 0. And I get negative 0.433 milliamps, positive 0.173 milliamps, and 0.433 milliamps. So my intuition was correct. We could have just simply used Ohm's law and gotten that current, but that dependent source is a little bit worrisome, so I didn't want to make any simple errors in judgment there. All right, so from this, we can see that VC at 0 plus is 13 volts, and I1 at 0 plus is 0.433 milliamps. Step 3 is to determine CEQ and REQ. Alrighty, so again, there's only a single capacitor in our entire circuit, so I'm going to go out on an adventuresome limb here and assume that CEQ is equal to 2 nanofarads because I literally don't comprehend how it could be anything else. To determine REQ, we are going to have to find the Thevenin equivalent resistance from the perspective of the capacitor. And so we're going to have a circuit that contains our dependent source, where this is 0.6 I1. Here's a 10 kilo ohm resistor. Here's a 20 kilo ohm resistor. Here's a 10 kilo ohm resistor. And let's see. This is my current I1. I have an open circuit here because we're during the transient condition means after the switch is opened. And because I'm trying to find the Thevenin equivalent resistance, I need a dead network, so my voltage source should be off. So I have a circuit that doesn't contain any independent sources, so I'm going to have to use the test source method here. All right, so test source method. I'm trying to look at this and see if it will be easier for me to apply a voltage source or a current source as my test source. And I believe pretty strongly that a voltage source here is the correct way to go. So I'm going to apply a 1 volt source, and that's equal to V test. I'm going to determine this current I test, and my equivalent resistance, REQ, will by definition be V test divided by I test. Thanks to good old George Simon Ohm. All right, so let me explain why I've chosen a 1 volt test source. Okay, 1 volt test source allows me to calculate the value of this current I1 here very easily. I won't need to do mesh analysis again. I feel very strongly that if I could use actually what's called the homogeneity principle of superposition. So if 13 volts gave me a current I1 of 0.433 milliamps, then 1 volt should give me 1/13 of this. But I'm just going to use Ohm's law to figure it out because it's going to be effectively the same thing. So if I know this current I1, then I know this current as well, and I can just do Kirchhoff's current law at that node to find I test. So what I mean specifically by that is that, let's see, so I test is going to be equal to, or excuse me, I test is flowing in, 0.6 I1 is flowing in, will be equal to the current that's leaving the node, which is I1. I can rearrange this so that I will have I test is equal to I1 minus 0.6 I1, which is 0.4 times I1, where I1 is 1 volt divided by 30 kiloohms. So 20 kiloohms plus 10 kiloohms, and I get 0.4 times 1 divided by 30,000. 13.333 microamperes. Okay, let me make sure. Yes, 13.333 microamperes. So again, to be clear here, what I did, I simply performed Kirchhoff's current law at this node, and then I used the results of the previous part we worked where I was able to determine that current I1 pretty easily just by using Ohm's law to get this result. So V test 1 volt divided by 13.333 microamps gives us 75 kiloohms. So REQ is 75 kiloohms, which, just to be clear, we would have never gotten by combining these 10 kilo ohm resistors and this 20 kilo ohm resistors. So the test source method is the way to find the equivalent resistance of a circuit that does not contain any independent sources but does contain dependent sources. So CEQ 2 nanofarads, REQ 75 kiloohms. And now we have step 4, where we just plug things into our generic expression, which is my favorite part because it's the easiest. And our generic equation is y of t is equal to y at 0 minus, excuse me, 4 t less than 0 minus, and y at 0 plus e to the minus t divided by RC for t greater than or equal to 0 plus. So let's start with our capacitor voltage. Vc of t is 13 volts for t less than 0 minus, and it's 13 e to the minus, so let's see. So 2 nanofarads, so that's 2 times 10 to the minus 9, multiplied by 75 kiloohms, so that's 75 times 10 to the positive 3. So that gives me 150 microseconds. If I take the inverse of that, so just to be clear here, RC is equal to 150 microseconds. So I could have t divided by 150 microseconds, or .667 t. So this is just the inverse of 150 microseconds. So if 150 is 300 over 2, this is 2/3 with the right factor. Anyway, let's see. 13 e to the minus 6666.667 volts for t greater than or equal to 0 plus. And my current I1 of t is 0.5 milliamps for t less than 0 minus, and then 0.433 e to the minus 6666.667 t milliamps for t greater than or equal to 0 plus. So the level of complexity in this problem was definitely increased from our previous example, but we were able to use the circuit analysis techniques that we've learned previously, nodal analysis, mesh analysis, Ohm's law, things like that, in order to get our different constituent parts of our final result and then plug them into our generic equation and go from there. So when we come back, we are going to start looking at first order circuits that contain inductors. Thanks for watching. Let's now talk about the behavior of first order circuits that contain inductors. So in this circuit, I have a current source that is connected to this RL network for all t less than 0 minus, and then at t is equal to 0, this switch closes from this terminal to this terminal, which effectively disconnects our source from the RL network. Now, at t is equal to 0 minus and before, our inductor is behaving as if it were a short circuit. That is its DC steady state equivalent. So it should be easy to see that there will be a current of IS that's flowing through the inductor L for all t less than 0 minus. Now the voltage drop over our inductor, VL of t, is equal to L times the derivative of our current, I of t, with respect to time. When this switch opens up, what we should observe is that, say, with our previous example with a resistor, the current through the resistor should instantaneously drop to 0. The problem with that is if our current changes abruptly from IS to 0, then this derivative term is going to go to infinity, and we'll see that we have an infinitely large voltage drop over our inductor, which means we have an infinite amount of current flowing through our resistor. And so we run into a situation again where our basic circuit analysis techniques tell us that we have 0 current and an infinite amount of current at the same time, which means we have a fundamental limitation of our model. So if we plot the behavior of I of t as a function of time, we know that for all t less than 0, it's going to have a fixed value. And then we know that at some much longer point in time, everything should settle down to 0. And again, this is a DC steady state condition over here. Steady state. This is a DC steady state condition. And we have a transient condition as our current changes from this DC steady state to this DC steady state condition. This relationship actually tells us something that's very similar to what we saw in our capacitors. The current flowing through an inductor cannot change abruptly, so it must be a continuous function. So this implies that IL at 0 minus has to be the same as IL at 0 plus. If that isn't true, then we get an infinitely large voltage, which means we are transferring an infinite amount of energy in an infinitesimal amount of time, which cannot happen. So we're going to approach our analysis under this constraint. We're going to write ourselves a KVL equation around this loop. When this disconnects, we're going to follow this current I of t around through the inductor and then back up through the resistor. And we find that VR of t plus VL of t is equal to 0 from Kirchhoff's voltage law. We can use Ohm's law and express the voltage drop over the resistor as R times I of t plus L di by dt is equal 0. And we're going to make a guess on the shape of our current I of t. Our guess will be the exact same thing it was in the case of an RC circuit. We have an exponential function with some unknown coefficient a, e to the st, where s is the eigenvalue or natural frequency of the system. If we substitute in our guess value, we get r, a, e to the st plus sl, a, e to the st is equal to 0. We factor out the common factor of a. We get r plus sl, e to the st is equal to 0. And again, we have a characteristic equation. So if R plus SL must equal to 0, then that means S is equal to negative R divided by L. So we can write this as A e to the negative R over L T. And this A coefficient is going to be, again, the initial condition. So this is going to be I at 0 plus e to the minus R over LT, so that generically, in a first order RL circuit, we see that y of t is equal to y at 0 minus for t less than 0 minus, and y at 0 plus e to the minus R over LT for all t greater than or equal to 0 plus. So this is the equation that governs the behavior of all voltages and currents in a first order RL circuit. Hopefully you all notice that this expression is extraordinarily similar to what we got for our capacitor equations, right? So the only difference there is that the coefficient that's being multiplied by t is different. And we are going to introduce the concept of a time constant in the next lecture to account for this. But let's first work a few example problems of RL circuits. This is our example problem that we're going to work to explore how we are going to analyze first order RL circuits. Now the first thing that you may notice is that this particular circuit actually contains 3 inductors. And by definition, a first order RL circuit only contains 1 inductor, or at least 1 equivalent inductance. So I'm going to take a moment here to explain how we could determine the equivalent inductance of this circuit. Notice that this 1 millihenry inductor and this 50 ohm resistor are connected in series. Because they're connected in series, we could simply switch those 2 elements without changing any of the information in the circuit. Right? They're in series, so it doesn't matter what order they're in. We also have this 2 millihenry inductor in parallel with a 3 millihenry inductor. So we could combine them into an equivalent inductance that is then in series with that 1 millihenry inductor, and we can see that even though there are 3 individual inductors here, they're all connected in such a way that we have a single distinct equivalent inductance. All right, so our analysis of this type of circuit is going to be almost identical to our analysis of first order RC circuits. Our first step is to analyze the circuit at t is equal to 0 minus. So at t is equal to 0 minus, this switch is closed. So we will have an 18 volt source. There's our closed switch. Here is our 90 ohm resistor, and the current I1 at 0 minus is flowing down through it. This 60 ohm resistor and this 120 ohm resistor are in series, so I'm going to replace that with simply a 180 ohm resistor. Also notice that this is a short circuit, so it's connected to the positive polarity terminal of the 18 volt source, and then the other leg of the 180 ohm resistor will be connected to the negative polarity terminal. So I can simply draw it as if it were in parallel like this without losing any information. Then I have a 1 millihenry inductor, which looks like a short circuit because we're at DC steady state, and a 50 ohm resistor. And then I have these 2 guys are going to be short circuits, and 2 short circuits in parallel looks like 1 short circuit. So this is my equivalent circuit. and this is my current IL at 0 minus. So I can determine what these two currents are actually very, very easily, just using Ohm's law. Because I have an 18 volt source in parallel with a 180 ohm resistor, in parallel with a 90 ohm resistor, in parallel with a 50 ohm resistor. So IL at 0 minus will be 18 volts divided by 50 ohms, which is 360 milliamps, and I1 at 0 minus will be simply 18 volts divided by 90 ohms, which is 200 milliamps. So this is our circuit analysis completed at t is equal to 0 minus. So we have IL at 0 minus is 360 milliamps, sorry. And I1 at 0 minus is equal to 200 milliamps. Now we'll analyze the circuit at t is equal to 0 plus. So at t is equal to 0 plus, this switch is opened, which is disconnecting the 18 volt source from the rest of the circuit. So I'm just no longer going to draw that. So I will have 180 ohms of resistance for my 60 and 120 in series. In parallel with my 90 ohm resistance through which my current I1 at 0 plus flows. Then I have my inductor, and we'll talk about what I'm going to do for that. And then I have a 50 ohm resistor, and then I have two more inductors. So let's first talk about our 1 millihenry inductor through which our current IL of t is flowing. We know that the current through an inductor cannot change abruptly. So if there was 360 milliamps of current flowing at t is equal to 0 minus, there must continue to be 360 milliamps of current flowing at t is equal to 0 plus. So I'm going to replace this inductor, the 1 millihenry inductor, with a current source because it has a fixed amount of current flowing through it at this particular instant in time, and the voltage drop over it will be whatever it needs to be to have 360 milliamps flowing through it. So the direction of IL of t is directed to the right, so the direction of my current source is to the right, and here is 360 milliamps, and this is IL at 0 plus. Now, for these other two inductors, we don't know how much current flows through each individual inductor. And because we were at DC steady state and we were treating them as short circuits, it would actually be extraordinarily hard to figure out a means by which to distribute that current. We do know that that 360 milliamps of current, when we're looking at this circuit at t is equal to 0 plus, flows through this resistor, and then the total amount of current that's flowing through this network has to be 360 on this return path. So I would argue that if we treat this like an individual resistor an individual equivalent inductance instead of two separate inductances will make our life easier. So we know that a combined total of 360 milliamps of current flows through this network comprised of the 2 millihenry and 3 millihenry inductor in parallel. And notice now that our circuit contains a 360 milliamp source in series with another 360 milliamp source. If we have two identical current sources in series, we can replace it with a single current source of 360 milliamps. So this is our most simplified version of the circuit at t is equal to 0 plus. So it should be fairly easy to see that IL at 0 plus must be 360 milliamps. Again, it can't have changed from its value at 0 minus. And we can determine I1 at 0 plus using current division. So the current is going to flow through all 360 milliamps of current will flow through the 50 ohm resistor and then hit this node, and it's going to split and divide itself among the 90 ohm resistor and the 180 ohm resistor. Because the and it's going to be flowing up. Because the current we're looking for is flowing down, we need a negative sign. So we have negative 360 milliamps. We want the current through the 90 ohm resistor. So that's going to be 1 over 90 ohms divided by 1 over 90 ohms plus 1 over 180 ohms, which is going to be 2/3. So 360 milliamps times negative 2/3 will give us negative 240 milliamps. So we have IL at 0 plus is 360 milliamps, and I1 at 0 plus is negative 240 milliamps. Our third step is to determine LEQ and REQ during the transient condition. So since we're during the transient condition, that means that that switch is opened and the 18 volt source is disconnected. So what we are going to have is the following overall network. We have a 180 ohm resistor, which is just this 60 and this 120 combined. In parallel with a 90 ohm resistor, we have our 1 millihenry inductor, and we have our 50 ohm resistor, our 2 millihenry inductor, and our 3 millihenry inductor. Now, the first thing that you may have noticed is that I don't have any open terminals to look through, and we'll get to that in a moment. I want to be very clear again about what we are trying to find. We are trying to find the equivalent inductance from the perspective of the resistance during the transient condition, and we're trying to find the equivalent resistance from the perspective of the inductance during the transient condition. So what I'm going to do is I'm going to swap these two elements because they are in series. So I'm going to move my 50 ohm resistor to the left. And I'm going to move my 1 millihenry inductor over to the right. And now I'm going to draw some terminals. Effectively, what I've done is I've grouped my resistors on one side of this set of terminals and my inductance on the other side of the terminals, so I can treat this as two different networks. This is network A, and this is network B. If you can remember what we did in our lecture on Thevenin and Norton equivalent circuits, To find the equivalent resistance of network A, we disconnected network B and looked in. So, ignoring network B as if it were entirely disconnected from the network and looking in from the right to the left, we would see that REQ, we have a 50 ohm resistor, and that is going to be in series with a parallel combination of 90 ohms and 180 ohms. So that's 90 ohms times 180 ohms divided by 90 ohms plus 180 ohms. I believe that this parallel combination gives us 60 ohms. So 60 in series with 50 looks like 110 ohms. Let me just double check the math on that real quick. That's correct. And to find our equivalent inductance, we're going to disconnect this resistor network and look in this way. So we'll see that LEQ is 1 millihenry in series with a 2 millihenry inductor and a 3 millihenry inductor connected in parallel. So that's 2 millihenries times 3 millihenries over 2 millihenries plus 3 millihenries. So that 6 over 5 is 1.2 plus 1 is 2.2 millihenries. So REQ is 110 ohms. LEQ is 2.2 millihenries. And now we are ready for step 4. Which is plug in our information into our general equation for RL circuits. Where we know that Y of t, which is any resistor, current or voltage, or inductor current or voltage in a first order RL network, will be of the form Y at 0 naught for t less than 0, Y at 0 minus for t less than 0 minus, and Y at 0 plus e to the minus r over LT for t greater than or equal to 0 plus. So from this, our inductor current, IL of t, is going to be 360 milliamps for t less than 0 minus, and 360 e to the minus. All right, so R over L is 110 divided by 2.2 times 10 to the minus 3. So that's 50,000. So minus 50,000 T milliamps for T greater than or equal to 0 plus, and I1 of T, our resistor current, will then be positive 200 milliamps for T less than 0 minus, and negative 240 e to the minus 50,000 T milliamps for T greater than or equal to 0 plus. So the process by which we analyzed our first order RL circuit is almost exactly identical to how we've been analyzing our first order RC circuits. The only difference came in step 3, where instead of finding the equivalent capacitance, we then instead found the equivalent inductance. That's going to be all for our first order source-free circuits. I'm saying source-free because in all instances that we've worked today, we have been disconnecting our independent sources from our inductor and capacitor networks. Our next lecture will be what's called the total response, which is going to involve what happens when we leave sources in or add sources to our inductor and capacitor networks. Thank you guys for watching.